Okay, hello. Today we're going to start talking about the solar system, right? So in this class, we're covering the solar system, then we're going to expand outward. We're going to talk about our sun, talk about the stars, then galaxies, then the universe as a whole. And so we're going to start local. We're going to start with an overview of our solar system, and then we're going to go into a little bit more detail over the next few lectures. Are there any questions before we get started? Okay, so, right, so as I've cautioned previously, you will see various representations of not only our solar system, but all sorts of astronomical objects and systems in this course, and in general in the media. And you need to be careful about how you interpret them, because for example, the distance scales and sizes in astronomy are so large that it's sometimes hard to show all of something at once. So this is a picture that gets some things very, very wrong. In fact, this gets pretty much everything wrong, except for the order of the planets. So this has the sun and our planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Looks like it also has Pluto there too. Okay, but it has everything else wrong. Okay, it has the distances between the planets wrong. That's pretty forgivable, because if you really did pull out their distances completely, you could hardly see them, right? But it also has their sizes wrong. Now, it has the relative sizes correct, but the absolute size, like Jupiter, is way bigger than the Earth, right? That's also sort of forgivable, because if you do show the sizes correctly, then Mercury will look just like a little dot. Okay, so people make these compromises to show one or another feature of the solar system. In this case, they're just trying to show the order and what the planets look like and their relative sizes, but it gets pretty much everything else wrong. Of course, they're also not all in a row, right? Here, at least at the top of the screen here, is a picture that makes several major compromises, such as it's not showing the correct distances between planets, and of course they're not actually in a row, but at least this one does show the relative sizes correctly. So indeed, right, Jupiter is the largest, then Saturn, Uranus, and Neptune. These are all composition, right? It turns out that there's an interesting pattern here. All of the rock dense planets are close to the sun, and then these big, less dense, gaseous planets are far away from the sun. Okay? And that'll also, we'll see that's true also with asteroids and comets. Asteroids are close to the sun, comets are far from the sun. Patterns of motion, right? They have all the planets, with a couple exceptions, as well as asteroids and comets, all orbit the sun in the same direction, and roughly all in the same plane. Okay? So this is what we're going to talk about over the next several lectures. So the first major thing that we notice is a pattern of composition. Okay, the inner terrestrial planets, that's the first four planets, Mercury, Venus, Earth, and Mars, are all dense. What do I mean by dense? That's mass contained in a volume. So something like gold is very dense, a lot of mass, just a little volume. But over here, the gas giants are not very dense. There's a lot of gas, which is not dense. Overall, their density is about similar to the density of water. Okay, their outer parts are very gaseous and very non-dense, but then once you get to the inside, they get denser. And overall, about the density of water. Whereas the interterrestrial planets are like 4 or 5 times the density of water. Earth is the densest. And you see here, Earth is just a little bit denser than Mercury. And then the asteroids are kind of in between, but generally pretty dense. They're very similar to the rocky terrestrial material. But then also out far away, we get the comets, which are made of stuff similar to the gas giant. So they're less dense. And we're going to understand later in this course, we're going to explain why this is, what causes this pattern of composition. But for now, I'm just explaining what that pattern is. Okay, next would be just understanding, the order of the planets, the scale of the solar system. The solar system is huge, okay? And we talked before about if you were to scale down the solar system by a factor of 10 billion, so that the sun is the size of a grapefruit, so the sun is like this big. Earth then becomes the size of the tip of a ballpoint pen, and that tip of a ballpoint pen is 15 meters from that grapefruit-sized sun. That's how to visualize the true relative scale, the size and distance of the Earth and the sun. And then the nearest star in that scale, if you have so you can make your own solar system. Put the grapefruit in a park, go 15 meters away, so 15 really large paces away, put a little tiny pebble for the Earth. But then if you wanted to get to the nearest star, you'd have to go all the way across the country, 4,400 kilometers away. So that's just gives you a sense for just how big even the distance to the nearest star is. So if you were to make one of these solar systems yourself, like in a park or something, grapefruit down, Mercury would be just 5 meters away, so 5 big paces. Earth would be about 15 meters away. Okay. Looks like there's a misprint here. This is probably 22. I'll have to fix that. Jupiter would be like 80 meters away. The furthest Neptune would be half a kilometer away. Okay. And then, like I said, the nearest star would be all the way across the country. And then here's their sizes, right? So if the sun is a grapefruit size, the biggest planet, Jupiter, would be like a little more. And here, if you overlaid it on the our camps, you get a sense for like a pattern of scale where you see, so green is Earth, red is Mars here. You see that all the terrestrial planets, these rocky terrestrial planets, are all way closer to the sun than starting here. Jupiter, Saturn, Uranus, Neptune are all really far away. And like suddenly, so these are all bunched together, and suddenly there's huge distances to get to Jupiter, to get to Saturn, Neptune, Uranus, Neptune. Okay, so even if a spacecraft takes over a year to get to Mars, that's just going between green and red here. But to get to Jupiter is way, way far. So here, if we'll zoom out. So here's the sun, Mercury, Venus, Earth, Mars in red, and then a huge jump all of a sudden just to get to Jupiter. And then another huge jump to get to Saturn. Zooming out. Another huge jump to get to Uranus, another huge jump to get to Neptune. And then you can see Pluto's orbit, which we now no longer call a planet, it's a dwarf planet. You can see how its orbit is a little irregular. So actually sometimes of the year, well, not sometimes of the year, every few decades, you'll hear about, just for a little bit, the Pluto is actually closer to us than Neptune. You see why? Because its orbit is a little bit more elliptical. It actually intersects Neptune's okay, and then if you keep zooming out, and this is not to scale, but here's the sun. Another pattern of composition is you have what's called the asteroid belt, where this is between Mars and Jupiter, where you have a bunch of this rocky debris that are the source of most asteroids in the solar system. And then past Neptune, we have trans-Neptunian objects, including the Kuiper belt, which is a belt of more comet-like material, which is more icy. And then this is the part that's not to scale, is the Oort cloud extends way further out past the Kuiper belt to the edge of our solar system. That just contains random orbiting debris that's mostly comets. Okay? But the asteroid and Kuiper belts, they're called belts because they orbit in the same plane as all the rest of the planets. They're like a belt shape. Any questions about just the scales in the solar system and the main, the order of the planets, the order of these objects? Because the next thing is a pattern of motion, right? So the planets all, with a few exceptions, not only rotate in the same direction, not only have their moons orbiting in the same direction, but also the planets themselves all orbit the sun in the same direction and in the same plane. If you take the North Pole of Earth and you imagine you're hovering above the solar system, above the North Pole, and you look down, the pattern of motion is to orbit and to rotate counterclockwise, as shown in this picture. So the sun is rotating counterclockwise, planets are rotating counterclockwise, moons are rotating counterclockwise and orbiting counterclockwise, and the planets are orbiting all counterclockwise.
Oh, okay.
So here it's showing all of that with just a couple exceptions, okay? One is that Uranus is tilted on its side. So that means that you can't really say it's rotating clockwise or counterclockwise, it's just on its side. Venus is rotating clockwise as opposed to counterclockwise. But that's basically because it's not rotating at all. It's very, very slow rotation. And finally, there's a moon, Triton of Neptune, that's orbiting in the wrong direction. But other than that, every single thing in the solar system is all orbiting in that same counterclockwise or rotating in that counterclockwise. So we're going to have a whole couple lectures on the sun, right? But as a very brief overview, as we go throughout the solar system, for each of its pieces one by one, the sun, of course, is the largest thing in our system. That's 99.8% of all the mass in our solar system. What is it made of? It's made of mostly hydrogen and okay? And it's in the form of what we call a plasma. Plasma is like a gas, but it's a little different from a gas because it's so hot. It's like a flame. A flame we call a plasma because it's so hot that the electrons are no longer orbiting the nuclei of atoms. They're all separated because they're so hot they don't snap together. The sun, in order to create its energy, is fusing hydrogen into helium. And in so doing, through E equals mc squared, it's converting 4 million tons of mass into energy every second. Okay? That is, it's losing 4 million tons of mass every second in order to produce all of that light. But don't worry, that it's not going away anytime soon. The sun is so massive that 4 million tons is this tiny, tiny, tiny fraction of the overall mass. So it's going to take another 5 billion years for the sun to run out of energy. But that's how it's producing energy. It's converting mass into light. The radius of the sun is very large physically. It's over 100 Earth radii in radius. So that's what these symbols mean. This means the radius of the sun is 108 Earth radii. 108 times the radius of the Earth. The mass of the sun is 333,000 times the mass of the Earth. The density of the sun is 1.4 times the density of water. Okay? Close to the same density as Jupiter, or the same density as water. Overall, near the surface of the sun, it's like very, very little stuff. It's plasma or a gas. So very low density, but when you get to the center, it gets really, really high density. So it averages out. You've got the density of water. So it's very large. You see Earth here to scale. We'll talk about all the features on the surface of the sun. It's a very interesting object, very hot, very active, very large. Okay, so I want you to know several of these things, right? It's about 100 times larger than Earth. That's about how large the sun is. What's the mass of this? It's about 300,000 times the mass of the Earth. And that's how massive the sun is. Very, very massive. That's why we're all orbiting the sun, because it's so massive. But that's the main source of gravity in the solar system. Okay, here's a question for you based on what I've just described about the source of energy on the sun. Ask a poll question. Right, how is Einstein's famous equation E equals mc squared important in understanding the sun? And I just went over. Maybe 10 more seconds. Okay, I'm going to end it. Okay, and the majority of people got the correct answer. As we were just describing, the sun generates energy through E equals mc squared by losing 4 million tons of mass. That's the M in this equation, mass, every second. Looks like quite a few people may have thought that that M stood for magnetic field. That's my best guess, and said answer A. But right, this is something I just talked about, and I didn't mention magnetic field. I didn't mention atmospheres of planets. Okay, so people who aren't paying attention, you're not going to get your participation credit. Okay, so just a fair warning. I'm doing my best to just kind of give you more or less free participation points, but you have to pay attention. Any questions about?
What did you say that the C stands for? I know E is energy and then M is mass, but what's C?
Yeah, good question. So C stands for the speed of light. So if you want to know how much energy for a given amount of mass, the M stands for mass. If you want to know how much energy for a given amount of mass, you multiply the mass by the speed of light squared. And I don't expect you to do that or anything, but what that tells you, because the speed of light is so large, that tells you that there's a huge amount of energy in just a small amount of mass. So you're multiplying the mass by a really big number, the speed of light, which is big, squared.
Why do we have to square it? Or that's just part of the equation? Why do we square it? Sorry.
Yeah, that's just part of the equation. I'm not going to go through the derivation of that formula, but yeah, that's just the equation. Any other questions? Okay, so that's a quick overview of the sun. Again, we're going to go in a lot more detail in a future couple of lectures. But let's give an overview of the terrestrial planets. We're also going to go into more detail in these next lecture. But as an overview, right, these are the kind of basically what they look like and their sizes in comparison to each other. So Mercury, next would be Venus, and Earth, and then Mars. One thing that I kind of like, so XKCD is a webcomic that a lot of sciencey types like me subscribe to or like and will recommend, because in addition to kind of funny comics, every once in a while this person comes out with a really kind of neat illustration like this. This is an illustration as if you were to stitch together the surface of all of the solid surfaces of the planets in our solar system, as well as big asteroids, moons. This is kind of what the planet would look, this is what a map would look like of all the surfaces So you can really get a sense for how much solid ground there is in our solar system. And that's what we're talking about here, terrestrial planets, right? The planets that have solid surface. And here's Earth, right? If we kind of stretch out all of the surface of the Earth, including Antarctica down here, right, and the oceans. But you see the next largest is from Venus, right? Big amount of surface from Venus. Venus is almost the same size as Earth. Next, you have Mars. Okay, so Mars is a pretty big planet. As we'll talk about, though, actually up here, these are the moons of Jupiter, the big 4 moons we call the Galilean moons of Jupiter, because they were discovered by Galileo. They're pretty big. I'll talk about those. Those are actually really interesting and exciting moons. Titan is a moon of Saturn. Asteroids here. Our moon.
Why you let her touch the computer?
Okay, but so you see, those make up the main terrestrial stuff, solar system. These first 4 planets: Mercury, Venus, Earth, Mars. And then we'll also talk about some of the moons of Jupiter are big, and there's some asteroids we'll talk about. Okay. But first, the terrestrial planets: Mercury, Venus, Earth, and Mars. Shown here, nice pictures of them with the correct relative sizes. And here's some basic facts. So Mercury, Venus, Earth, Mars have these diameters. So you see that if Earth is, distances from the sun. So if Earth is 1 unit of distance from the sun, Mercury is about 40% of the distance of Earth from the sun. Venus is 72%. Mars is 50% further from the sun than Earth. Here are their sizes. So if Earth is 1 unit of radius, Venus is 95% the radius of the Earth. So very similar size. Okay. Mercury is 38% the size of the Earth. Mars is 53% the size of the Earth. And their masses, okay? Earth is the most massive. Venus is 80% the mass of the Earth. Mars is 11% the mass of the Earth. Mercury is pretty small. It's only 5% the mass of the Earth. Here we have their tilts. So most objects in the solar system, I said they're rotating in the same direction. Well, Venus is one exception. So how do we talk about how they're rotating? Well, if we say the tilt is 0, it means that the axis of rotation is pointing up towards the North Pole, which we define to mean the planet is rotating counterclockwise about that axis. Okay. So Mercury is rotating exactly counterclockwise. Earth is rotating counterclockwise, but with a tilt of 23 degrees. Right? We talked a lot about that in the second or third lecture. Mars, remember, this is what gives us our seasons. Mars has a similar tilt. Venus is tilt all the way 180 degrees. Okay? In other words, it's rotating clockwise rather than counterclockwise. But it's rotating very slow, as we'll talk about. So it's almost like it's not rotating at all. Okay, another interesting thing is their temperatures, right? So, we'll talk a lot about the atmospheres of planets in a little bit, because it's interesting that you would think that the closer to the sun you are, the hotter you be. But actually, Venus, which is further than from the sun than Mercury, is actually the hottest planet in the solar system. Both day and night, it is 740 degrees Kelvin. In other words, it's like the temperature of an oven, day and night. Mercury is almost that hot during the day, but because it has no atmosphere, it gets really cold at night. So it gets freezing at night. Okay. Earth on average is 290 degrees Kelvin. That's about room temperature. And then Mars is colder than Earth, but still not nearly as cold as
Just go math class.
And then here's just some other characteristics, like a year on Earth in units of 1. Venus has a shorter year. Mercury has an even shorter year than that, a quarter, like 3 months. It's a year on Mercury. And Mars has almost twice as long. And what this says here, the inclination, it says that within a few degrees, all of these planets are all moving in the same plane. Okay? Mercury is tilted only 7 degrees, so it's almost hardly noticeable from what we call the ecliptic sun. So those are the main features of the terrestrial planets. Also, here's their density. So they're all, this is another pattern of composition. All these terrestrial planets are dense, about 5 times the density of water. Earth has the highest. Okay, so going through each of these. So Mercury, the closest to the sun, smallest planet, it's the innermost planet closest to the sun. No atmosphere, so you can't breathe on Mercury. It's just a vacuum of space out there. It's made of metal and rock. Has a large iron core. If you were to dig deep down, it's desolate. It looks like the moon. It's cratered. Has long, tall cliffs, and because it's the closest to the sun, it actually experiences the strongest tidal force from the sun. Now, remember, we talked about the tides on Earth are due to both the moon and the sun. They both tug on the Earth and kind of stretch the oceans towards both the moon and the sun. But Mercury is the closest and has the strongest tidal forces. And we'll talk more about tidal forces as we go on in the course, but this is the reason why. So the tidal force between the moon and the Earth is why the moon always has the same face facing the Earth. Basically, the Earth tugs on the moon so that it kind of keeps the same face facing the Earth. The sun does the same thing to Earth, and it's not exactly the same, but it has a similar what we call resonance. So between the Earth and the moon has a 1-to-1 resonance. It rotates once for every orbit around the Earth. Mercury has a 3-2 resonance. That is, it does 3 rotations for every 2 orbits around the sun. So its rotation period, how long it takes for a day to pass on Mercury, is 58 Earth days. And its orbital period, it's a year on Mercury is about 88 Earth days. And notice that a day on Mercury is pretty long, 58 days. Earth days. No. That is, it's rotating pretty slowly. So that's this long day of like 3 months where it's really hot, hotter than an oven. And another 3 month long night that's super duper cold, almost as cold as outer space. So not a very hospitable planet. There's a really nice picture from satellites that we've sent to orbit around. Very beautiful, but desolate crater. Looks similar to the moon. Venus, similar in size to the Earth, similar in mass to the Earth. Okay? This is a symbol for Venus here. It's a symbol for Earth. Now, if you just look at it in visible light, you can't see the surface. It's covered in thick clouds of sulfuric acid. So it's another very non-hospitable planet. And it has an extreme greenhouse effect. It's the same greenhouse effect that people are worried about when we talk about global warming on Earth, which we will talk about in this course. Venus, it's a really strong effect. And this is why it's hot, both day and night, and 740 degrees Kelvin. So really hot, hotter than your oven, day and night. The pressure is really high, thick atmosphere, carbon dioxide, along with sulfuric acid, 90 times the pressure on the surface of Venus compared to Earth. So you'd be crushed if you like going deep down in the ocean. That's how strong the pressure is. It's how thick the atmosphere is. It rotates backwards, as we talked about. It rotates clockwise as opposed to counterclockwise. And it rotates really slowly, so it's almost not rotating at all. It takes 240 Earth days for 1 day to pass through Venus. Now we can see, using other methods besides visible light, use radar, for example, to look below the surface of Venus. We see it's made of rocks, metals. It's dense, like similar to Earth. No moons, so neither Mercury nor Venus have moons. So here, if we do look below the surface of Venus using radar, we see big mountains from volcanoes, lots of essential. So here, red is higher, blue is lower. Okay, so very volcanic, mountainous, rocky terrain. But here's the surface. You can see the movement of the sulfuric acid clouds rotating around the surface. Okay, Earth. Okay, here's a wonderful picture from Apollo 8. This was the mission right before the moon landing, where they orbited the moon and caught. So here they're just orbiting above the surface of the moon, but they caught Earthrise, so Earth rising over the surface of the moon. And you see that it's blue, which is very different compared to other planets, just because of the liquid water, which is kind of unique for the Earth. The swirling white clouds, also from the water. Okay, kind of a unique thing about the Earth is it has a large moon, just one. Has an atmosphere that contains oxygen and ozone. Oxygen is a kind of signal that Earth has life. Okay, we'll talk about the Earth and all of these properties more in a dedicated lecture. And one thing we'll talk about is the greenhouse effect, how it's modern. Okay? It's really important that the Earth has a greenhouse effect that keeps us from turning into a ball of ice. But it's also really important that it's not like Venus's greenhouse effect, right, which would make it like an oven. So it's a delicate balance that keeps the surface, the North and South Pole have ice, but the whole Earth isn't covered in ice. It's just the right temperature. The densest planet made of rocks and metals. Mars, okay? It's about 50% further from the sun compared to the Earth. It's about half the size of Earth. About a tenth of the mass of Earth. Has huge volcanoes, okay? Some of the largest volcanoes in the solar system. Not active anymore, but remnants of those volcanoes. Has huge canyons. The hugest canyon in the solar system, but not made. We'll talk about water on Mars, but not made by water, just because the planet at some point in the past developed fissures. But Mars has lots of evidence of geologic activity. So those volcanoes are an example. The fissures in the planet are evidence of geologic activity. And we'll talk about the fact that you don't see craters. Right? Why do you see all these craters on Mercury and on the Moon, but not Mars? Okay, that's because of geologic activity. We'll talk about resurfaces. Okay, there's polar ice caps. Those are mostly dry ice, CO2 ice. But we do see that there actually was water in the past that flowed. And as a result, we think that there could be life on Mars. There's actually some new missions that are going to be landing on Mars this year. That maybe that'll be interesting to talk about when that happens. Mars has two tiny moons, almost more like asteroids, Phobos and Deimos. Here's a picture of Mars from Hubble. You see the ice caps. Here's a much nicer picture from Viking, which flew by around Mars and could take much better pictures because it was close up. This is this enormous canyon. It's kind of ripped across the surface of Mars. You see these volcanoes here, and these little canyons here are evidence of past flowing water on the surface of Mars. And so one of these observations that we'll talk about in more detail next lecture is that Mars was probably suitable for life in the past. There's actually a really interesting story that we'll talk about in the future about how Mars lost its water. If it had all this water, where did it go? Okay, but now one of the pieces of evidence that we have that tell us that there probably was water flowing on Mars is that there are dried up riverbeds, things like these riverbeds that we can see. In fact, this sedimentary rock we can see that are in the riverbeds. The fact that the rock builds up in rivers the same way, and oceans the same way they do on Earth. You see on Mars. Okay. Some other things that I'd like you to know about what we've covered so far. Which planet has the densest atmosphere? Okay, that's definitely Venus. Mercury has no atmosphere. Mars has a very, very thin atmosphere. Earth has a substantial atmosphere with a moderate greenhouse effect, but Venus has a really, really thick atmosphere with an intense greenhouse effect. The pressure on the surface of Venus is 90 times the pressure on the surface of the Earth. That's how much atmosphere it has. Here is another question. This one I'll ask you as a poll. And that's, which of the following is not a characteristic of the inner planets? Given everything we've talked about today, which of the following is not a characteristic of the inner planets? So we talked about how how some have moons, some don't. We talked about how some have atmospheres, some don't. Which is not a characteristic of the inner? Okay. 5 more seconds.
Hey, Professor, you said we picked the wrong one. We can't repick one, right?
Correct. That's a limitation of Zoom polling. Okay, ending the poll. So most people got this one right. So I like how people are doing on this one. Yeah, so some of the planets have atmospheres, like Venus and Earth. Some don't, like Mercury. So they don't all have atmospheres. So that was D. That was the correct answer. So if we go through these, it is true that they're all smaller than the outer planets. We saw pictures of that, right? These tiny, dense terrestrial planets, and then these outer big Jovian planets, which we'll talk about next. They all have solid rocky surfaces. Their orbits are closely spaced. You saw pictures of that. So Mercury through Mars, all pretty closely spaced, and then suddenly big jumps to get to Jupiter, Saturn, Uranus, Neptune. And while the Earth has a moon, and Mars has a couple tiny moons, Mercury and Venus don't have any. So in general, they don't have very many satellites. We'll see that's a difference as we go to the outer planets. They have lots of moons.
That's what I meant.
Can you repeat that one more time? Sorry, because I got that one. I thought it was E, and it wasn't.
Yeah, so it's true that the inner planets have few satellites, meaning few moons. So Mercury has no moons, Venus has no moons, Earth has 1 moon, and Mars has 2 very tiny moons. So it's true that the inner planets have few moons.
Okay, I just wanted to clarify that there was a few, but okay.
All right. Any questions about the inner terrestrial planets so far? So, so we're exiting the inner planets now and moving towards Jupiter, but there's something in between Mars and Jupiter. Okay, it looks like there could have been a terrestrial planet there, but instead we don't see one planet. We see a huge belt-like ring of debris that we call the asteroid belt. That's shown here. So we're tracking as many as we can. So here's the orbit of Mars, here's the orbit of Jupiter, and there's this huge debris field called the asteroid belt between Mars and Jupiter. About 75% of the asteroids are in this asteroid belt. Some are also called Trojans that are in the orbit of Jupiter. Those are shown here. There's also some asteroids. You see there's some, not as many, but some are even inside the orbit of Mars and get close to Earth. We call those near-Earth asteroids. We're tracking at least 18,000 of them. And of those, right, some fraction of them can potentially intersect with Earth. So it's important for us to track those because we want to have warning about an asteroid potentially impacting us. Now, if we discover it early enough, there's maybe something we can do about it. But if we need a lot of time to potentially do something about it. And for really big asteroids, there's nothing. We'll talk more about that.
Yes.
It's wonderful to be alive right now because we're living at a time when we're actually sending satellites to go land on asteroids. And we're getting wonderful photographs like this. Here's a rover hopping on an asteroid. So here's the surface of the asteroid it's hopping around on. It actually scooped up a sample, returning to Earth, the asteroids. We'll see a number of photos like this, of course, which is cool because it's only something happening in the last few years. Now, asteroids, there are thousands of huge asteroids, but there's uncountably many like little pebbles and grains of dust. And in fact, there's at a certain point, we can't count anymore because they're too small. So what you see is that, we can definitely count pretty much all of the asteroids, well, not all of them, but many of the asteroids that are larger than a kilometer. That's what you see in the lower right. Kilometer-sized asteroids, about 1,000. But you see more and more, down to like 30-meter size asteroids. So like we were tracking like 5,000 near-Earth asteroids that are, the size of a bus or larger. But they get harder and harder to see. Okay. And of course, there's going to be thousands and thousands of asteroids that are smaller than that, like just the size of a baseball or the size of a meter, size of a car. But we can't see them. They're too hard to see. And we don't tend to care about them too much anyways, because they're not going to destroy the Earth. So we're not counting very many of these. But these are the ones we care about. All of these near-Earth asteroids that are at least, say, 30 meters in size. We keep discovering more and more because we get better at them, but it's hard to see things that are small because they don't reflect a huge amount of light. Here, so we're going to talk about the biggest asteroid in a second. This is starting with the second largest asteroid, and then all the other large. So these are the largest asteroids that are not dwarf planets. So one of the asteroids is a dwarf planet. But these are all of the asteroids from largest, starting with the largest non-dwarf planet asteroid. And you see that this one's almost round. Okay, and then these are all just kind of big, lumpy potato shapes. And the reason why this one's round or close to round is because there's enough gravity that it can pull it into kind of an almost spherical shape. That one's called Vesta. So where are most of these asteroids found? They're found in the asteroid belt between the orbits of Mars and Jupiter. We'll be talking about this later, the Kuiper belt, and we'll talk about the Oort cloud. It's also a source of comets, not so much asteroids. And we'll go into more detail about asteroids, but are there any questions now for our overview?
What kind of rotation does an asteroid have? Like, is it fast? Is it just kind of random?
It's pretty random, yeah. So when we talk about this pattern of motion, how all the planets and their moons are all orbiting or rotating in the same direction with the north poles all pointed mostly up. Once you get to the level of asteroids, they're all just rotating pretty randomly. Now, they're orbiting, though, in general, in that same pattern of motion. They're all orbiting in that kind of belt, that ring. Most of them are orbiting counterclockwise in that plane. Okay. Well, later we'll talk about the Oort cloud, where there's comets that are all just orbiting totally randomly, but the asteroids really are orbiting in that plane, counterclockwise motion. But because they're all colliding together, there's so many of them, and they're just colliding together, and they're small, so that they can just smash into each other and then start rotating in random directions. Yeah, the rotation tends to just be random. Any other questions? Okay, so next I want to talk about the outer gas giant or Jovian planets. So there they are. They're much larger than the terrestrial planets. They're different because they're not terrestrial, meaning they don't have surfaces, Earth-like surfaces. They have surfaces of gas. Okay, so we call them gas giants. They're big and gaseous. They have much further distances, remember, from the sun. So Jupiter is 5 times the distance of Earth from the sun. Saturn is 10 times, so now twice as far as Jupiter from the sun. Uranus is twice as far again, 20 times the distance of the sun. And then Neptune is 30 times the distance of Earth to the sun. So huge distances. Here are the sizes in terms of the size of Earth. Jupiter is 11 times the size of Earth. Saturn 9 times. Uranus 4 times. Neptune 4 times. So they're all much larger than Earth. They're all much more massive than Earth. Jupiter is by far the most massive. Jupiter is more than 300 times the mass of the Earth. They all have much lower densities, right? Which is, on average, they're about the whereas terrestrial planets are 5 times as dense.
Megan, just shut up,
this one exception of Uranus, they're all pointed more or less towards the North Star, meaning they're rotating counterclockwise with their axis pointing roughly upward. Uranus is one of these, the small number of exceptions in our solar system that it is tilted on its side. So it's rotating, but it's tilted on its side. We think that was because of a collision at some point early on in the solar system's formation. When we talk about their temperature, we're talking kind of like the clouds near the surface, right? Because the temperature changes as you get towards the center, but much colder. Okay, so you wouldn't want to live on Jupiter, and as you get further and further away from the sun, it gets colder and colder. Very, very cold on Jupiter, Saturn. And what are they made out of? So, right, they're not so much made of rock and metal like the terrestrial planets. Now, they do have a little cores of rock and metal in the center, but mostly they're made of the stuff the sun is made of, hydrogen and helium.
Get your book.
And then for Uranus and Neptune,
Get your book.
there's also a lot of hydrogen ice, we call them. That is, it's cold enough that they become ice, but water, ammonia, and methane. Notice that they're called hydrogen ices because they have hydrogens. Water is H2O, ammonia is NH3, methane is CH4. So a lot of hydrogen, because hydrogen is the simplest and most common element in our solar system. The sun is mostly hydrogen. These Jovian planets are mostly hydrogen. Okay, and like I hinted there, Jupiter and Saturn are mostly hydrogen and helium with cores of other stuff. Uranus and Neptune have mostly, are a little bit different in that they have, instead of so much hydrogen and helium, they have lots of these hydrogen compounds, water, methane, and ammonia.
Run in the room.
And then again, at the cores, they have some hydrogen and helium.
You're sitting on my spot.
But for both of these planets, the majority of them are
They will get
hydrogen,
the
helium,
workbook from the room.
water, methane, and ammonia.
Do this in there, please.
So Jupiter,
Please.
largest planet, most massive planet, no solid surface, mostly hydrogen and helium. 5 times the distance from Earth to the sun. So now we're getting very far away from the sun. Again, 300 times the mass of the Earth, 11 times the size of the Earth, density similar to water, has a huge number of moons. And I mean, we keep discovering, I mean, this probably isn't the end of the story. It's more than 79 moons we've discovered. Some of those are really big. We'll talk about those, the Galilean moons. And then there's lots of captured asteroids and just junk. And it has rings. All of the Jovian planets have rings. Okay? Saturn is the most visible, but all of them have rings to some extent. We're getting beautiful pictures of Jupiter from missions that have flown by it. Because like even with the Hubble telescope, it's hard to get a good picture of Jupiter. It's so far away, you have to fly by it. And luckily we have to get really nice pictures of Jupiter. Here's a image, it's composite. So this is an image of Jupiter with its ring. And this is as seen from above the surface of Io. This is the closest Jovian moon to Jupiter. And we'll talk about how Io is very volcanically active. That's what's shown here, is light being emitted by particles from a volcano that's interacting with the magnetic field from Jupiter, and so it's lighting up. And we'll talk about that. But yeah, that's Io, the first of these 4 Galilean moons, named after Galileo, who discovered them with his telescope in 1610. These are fascinating and very large moons.
You can't
Io
go
has
on.
very active volcanoes. That's this one.
Oh
Europa
my goodness, you sit up.
is a prime candidate in our solar system for life. Ganymede is the solar system's largest moon. It's also probably has a subsurface ocean, potentially a place where there could be life. Callisto is a cratered ice ball, but even it could have a subsurface ocean. We'll talk about what warms these things up to give them a subsurface ocean. It's because Jupiter is so large, it has a strong tidal effect on these planets, which causes them to kind of squish, get cold, and warmed up by friction.
Stop playing with my bear.
Saturn, okay, so next after Jupiter is Saturn. Similar to Jupiter, not quite as large, has these prominent rings. Okay, we'll talk about those. Huge number of moons, just like Jupiter. So again, we're probably not done counting, but at least 82. Again, we've flown by these planets with these space probes that have taken wonderful pictures. Here we're getting a nice view as Saturn is being passed, just showing just how thin its ring is. In fact, if you're straight side on, you can hardly see its ring at all. It's very thin. Titan has a large moon Titan, in addition to its 80 other moons, showing it transiting Saturn there.
Why are you picking your nose? It's one of the flats.
Here's a nice side-on edge view of Saturn with 5 of its moons. So here's Janus, here's Pandora, kind of in its rings, Enceladus, Mimas, and Rhea. You don't see Saturn. Saturn's off to the right. You see its very thin outer ring. If you were to zoom in on its rings, this is kind of what it would look like. Now, it's so small, like these rings are so thin that our probes haven't gotten so close to take an actual photograph where you can see this. But this is if you were to zoom in on its rings. This is an illustration that it's most likely kind of rocky clumps of icy dirt. But you have to understand the scales, the distances are so huge. Saturn is 10 times the size of Earth. Okay, these rings are many Earths distance out from Saturn. These rings are very thin, and you would have to get incredibly close to actually see them. You have to get dangerously close. Uranus. So as I said, all of these outer Jovian planets have rings. Uranus has rings. Now, this looks weird. It's red here because it was taken using infrared light from a different telescope. It had to take a long exposure photograph, and then it was superimposed on the same. Because now we're so far from the sun that it's everything is so dark. So it's very hard to see the rings of Uranus and Neptune. But this is what they look like. Also many moons, at least 27 moons. Again, as we get further out in the solar system, it's harder and harder to see dim objects that are far away from the sun. So we're definitely probably not done counting those moons. And again, what the ring shows you here, and also you can kind of see the pattern of the clouds, is that it's tilted on its side. And Uranus is tilted on its side. This is one of these few exceptions in the solar system. Venus, Uranus are orbit rotating, not like everything else. Uranus is tilted on its side. Okay, here's Uranus and one of its larger moons, Ariel. Again, another like superimposed long exposure photograph of its rings. Also another view with a long exposure photograph of its ring. Here you're seeing an aurora on Uranus. Okay, aurora, right, like on Earth, you go towards the northern or southern pole. You can see these beautiful lights in the sky called aurora, and they're related to the fact that we have magnetic field on Earth. This tells us there's magnetic field on Uranus, moving around as it orbits, as it rotates. Aurora. Okay, Neptune, the furthest official planet from the sun. Okay, at least 13 moons have been counted. Again, it has rings. It's this beautiful blue color due to methane with these clouds, white clouds that are giving it some kind of texture to its color. And then the third exception to the patterns of motion in the solar system we'll talk about is Triton. So Neptune has a moon Triton that's orbiting it in the opposite direction. So it's orbiting clockwise rather than counterclockwise. That's probably because it's a captured asteroid. Neptune, interestingly, just recently it was kind of celebrated, completed one full orbit around the sun. It's something like 160 years for it to go all the way around the sun. And that was kind of marking, one full orbit around the sun. Of course, it's done many orbits around the sun. Well, one full orbit around the sun since its discovery. So since its discovery, it's now done one full orbit around the sun. Remember, as you get further away from the sun, planets orbit more slowly. And here you're seeing its seasons. So as it orbits, it has seasons, just like the Earth does. But it takes many, many years for those seasons to show up. So here's just showing kind of averages as it rotates, what it looks like, and how as the seasons change, you get different cloud patterns as it gets colder in the northern and southern hemispheres. You get similar things as what happens on Earth show up, where more clouds are forming at different altitudes. Okay, here's those clouds showing up. It's kind of whitish clouds over the surface of Venus showing up in photographs. As you can see, the images start to not be quite as good when we view things like this. This is probably a Hubble photograph, because it's as good as Hubble can do, looking at something as far away as. But we did get a few good photographs when something like a Voyager probe passed by. So from 1989, Voyager probe passed by and got really nice pictures like this showing these cloud tops. Which of the following is not a major difference between the terrestrial and Jovian planets in our solar system? So here's just kind of an overview I want to give of some of the features of terrestrial and Jovian planets. So major differences. Terrestrial planets do orbit much closer to the sun. In fact, they're kind of bunched together in close orbits. Then you have this far away, spaced out Jovian planet orbits. So that's true. Terrestrial planets, one of their defining features is that because they're made out of rocky stuff, they have higher densities than the Jovian planets. So that's true. I'll skip this for a second. Jovian planets do have rings and terrestrial planets don't. That's true. What's not true of these is that terrestrial planets contain large quantities of ice and Jovian planets do not. It's the opposite. Jovian planets contain a huge amount of ice and by ices, we mean not only water ice, but methane and ammonia, hydrogen compounds that freeze and at those cold temperatures. One thing I want you to do, like on quizzes and stuff, I want you to be able to rank things. I want you to be able to rank the distance of planets from the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, but also by size. Okay? You should know, Mercury is the smallest, then Mars, then Venus, Earth. This you can remember because we talked about the terrestrial planets. So first is the terrestrial planets, they're all the smallest. It's Mercury, Mars, Venus, and the Earth is the largest. And then of the largest planets, these are the hard ones. There's basically the same size. But there's nothing tricky in this list. So you know that these come next, and then it's Saturn and Jupiter. Jupiter's the largest.
Go to his room, he's in class right now.
What's beyond Neptune? Okay, we call these trans-Neptunian objects, things that are past Neptune. And we talked about the asteroid belt. Well, past Neptune, you still get kind of some junk. You get some asteroid-like stuff, but mostly it's stuff that's more similar in composition to the Jovian planets. That is ice-rich, lots of ices. These are two things that are too small to gravitationally hang on to, so they're not just like mini gas giants, but they're the ices that are frozen, and so they can form like chunks of ice balls, like this here. This is, again, I promise that there's these wonderful things just happening in the last few years where we're sending up probes to actually look and even land on comets and asteroids. So here's a comet up close. So there's a comet right here. It's kind of a weird dumbbell shape, like two ice balls smashed into each other. You see it's kind of some outgassing coming off. In other words, comets start developing a tail as they get close to the sun. They heat up and evaporate. So this is a selfie from the Rosetta probe. This was a moon of a comet. Moon of a comet that an amateur astronomer discovered. So here's the comet, the one we were just looking at, that has, I'll go back to see this. An amateur astronomer noticed that it actually had a little moon. So it's a moon of an asteroid. Anyway.
Wasting things, guys. Like, I hate wasting food.
Okay.
I hate wasting food.
So once you get past the Neptune, you enter a region where you still have a belt of stuff that could have formed a planet out there. Among them is Pluto, but it's all ice rich, so it's filled with comet-like stuff. That's the difference between asteroids and comets. These are things that are rich in ice. And we call this belt of stuff the Kuiper belt. So past Neptune, we have this belt, like the asteroid belt, but it's more comets. Okay, and then all surrounding and way past that, until the edge of our solar system. And it's not to scale, so it goes way past the Kuiper belt, all the way up to a light year. It's called the Oort cloud, and this is just the remaining random debris that's not in the same orbital plane as everything else. It's just all random directions with comets, mostly, that are very far away on average from the sun.
I hope I don't ruin my goddamn
Here's just image showing all the stuff we're tracking, right? We have databases trying to track all this stuff. So there's the sun in the center.
What are you doing?
Jupiter and Saturn in blue, and then in pink, these are the asteroids that we're tracking. Okay, and there's also some stuff in orange that aren't in the asteroid belt that we're tracking. But then in green, this is the Kuiper belt. So past Neptune, you have this ring of debris. It's mostly comet material. And these trans-Neptunian objects include Pluto. Okay, Pluto used to be a planet, but we decided because it hasn't cleared away that debris field, and there's a ton of other stuff of similar size now that we have better telescopes and can see, things like Eris, Makemake, big stuff out there.
I heard it's some extra
We
spicy.
no longer call it a planet, we just call it a dwarf planet. There's other dwarf planets like Eris out there. So there's a list, there's a whole bunch. We just keep discovering them more because they're so far away that they're very dim, they're hard to see. So there's probably many more very large objects out there, but we don't call them planets because they're just among this huge debris field. We just call it the Kuiper Belt. For comparison, here's the size of the moon. Part of Pluto, Eris. And here is just kind of an overview showing all of the stuff in our solar system, where on this direction shows you the distance from the sun, so the distance from the sun, Saturn, Uranus, Neptune, then Kuiper Belt
Did
here.
you tell Venus to go class?
And here on the y direction axis is the inclination of the orbit. So in other words, most of the stuff is pretty much all in the same plane.
You Venus, go to class, man.
Within 10 degrees. So you see how most of the stuff is within 10 degrees. But when you get further and further out, you get more and more irregular stuff. So Pluto, for example, is almost 20 degrees outside of the plane of all the other planets. So it's starting to get a little weird. Eris is pretty weird. It's really
I feel like
a big dwarf planet out there that's part of what we call the scattered disk past the Kuiper Belt. But all of these things past Neptune, the subpart of the Kuiper Belt called the Plutinos, the Kuiper Belt, the scattered disk, all this we just call trans-Neptunian objects.
You know, that's just nice.
Here you're also seeing those sizes, illustrated. Okay, here's Pluto. Actually, luckily, we've just recently had a nice flyby to actually start to see some of its surface. The surface is interesting. It's very cold there. It's mostly just those are mountains, but they're just mountains of ice. It's all just a giant comet in a way. A very interesting landscape. Okay.
We haven't done one of these in a while.
As an overview, the solar system has two major patterns of composition: rock and metal for terrestrial planets. Those are the innermost planets. And the outermost planets are ice and gas. We call those the Jovian planets. And you have all these swarms of smaller bodies. The rocky metallic stuff are called asteroids. Ice. And for the most part, everything is moving counterclockwise and rotated counterclockwise when viewed from the north celestial pole. Viewed top down. Just three exceptions: the rotation of Venus and Uranus, and Neptune's moon.
You can do something like that.
So to explain these exceptions again, we kind of expect that you'll have things smashing into each other. Some moons were really just captured asteroids that knocked in and fell into them. So there's these few exceptions: the Venus, Uranus, Triton. Also, the fact that Earth, even though all the other terrestrial planets don't really have moons, Earth has a large moon. We'll learn that that's also kind of an accident due to a collision. But what this is pointing towards is something we'll discuss in some detail, which is that the origin of these patterns is asking for an explanation, right? What is the origin of all these patterns? Why? Well, it's because the solar system all formed from the same thing. Okay? It was all one swirling cloud of gas and dust at some point. So we'll tell that story, okay? But these are the few exceptions that you expect, because over time there's going to be some collisions and stuff. But overall, these patterns exist for a reason. I'll leave you with this today. One more reminder about something we covered in this class. Which of the following is furthest from the sun? Well, Pluto's pretty far from the sun. It's usually further than Neptune. Definitely not the asteroid belt. That's mostly between the orbits of Mars and Jupiter. The Kuiper belt is past Neptune, but even further is the Oort cloud. The Oort cloud extends to the furthest edges of our solar system. And that, the things in the Oort cloud would tend to be the furthest from the sun. Okay, we'll go over some of those. So just other reminders. Yeah, the hottest planet is Venus. The densest planet is Earth. We'll go over those again at the beginning of the next class, where we're actually going to go into more detail about terrestrial planets specifically. Do you have any questions before I let you go?
So the next class, we're gonna start chapter 6, right?
I believe this is chapter 6. I think chapter 5 was light, so this should be chapter 6. Yeah, the formation of the solar system. Yep.
So that's gonna be part 2 of chapter 6 next week.
No, next week we're going to start covering chapter 7. That's going into the terrestrial planets specifically in more detail. And this should all be given on the course webpage, remember, because not only the lecture notes, but the chapters that are being covered and the readings. All right. I'll see you on next Monday. Thank you, Professor.
Have a great day.
You too.
Thank you. Thank you.
Can get a piece of paper.
Baby, hush.
Shut up. You in class, what you doing? Huh? Did you finish your assignment? Huh? Your 10 minutes was, you're not 10 minutes for you to eat, man. 10 minutes to do your assignment, y'all.